Hey, you are welcome back to my calculus class. Briefly, this time we are going to be looking at the limit laws, and we are trying to cover all these subtopics by first recognizing the basic limits law. We will use the limit laws to evaluate the limits of a function. We will evaluate the limits of a function by factoring and using those laws to evaluate limit of polynomial and rational functions. We will also evaluate limit of a function by factoring or by using conjugates. And lastly, we will evaluate limits of functions by using the squeeze theorem. Let us quickly revisit something we learned from our last class. I have given you this basic limit results. But let me quickly remind us how we got that result. If we have, let's say, a function f of x equals to x, a linear function, which behaves this way. Now, if I ask you, suppose this is 3. If I ask you that what is the limit? Okay, before I ask you that, let us feel, let us draw the graph. Maybe we should do it this way so that you can see it clear. So if I have f of x equals to x, I can make table of values, x, f of x. If my x is -2, f of x is -2 since f of x is x, right? If it is -1, it is -1. If it is 0, it is 0. If it is 1, it is 1. If it is 2, it is 2. And so on. So let's say this is 1, 2, 3, -1, -2, -3, 1, 2, 3, -1, -2, -3, and so on. When x is -2, y is -2. Something like this. When x is -1, y is -1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. Okay, we have a straight line. We have a straight line. All right, now, if I ask you that, um, let me, oh shit, okay, let me make this way, 1, 2, good. So if I ask you that, what is the limit? If I ask you what is the limit as x goes to 2 of our function f of x, which is x, you would see that now you will look from the right, you look from the left. As you are moving from the right, the y value is trying to get to 2. As you are moving from the left, the y value is trying to get to 2. If I change that, so it is 2. If I change that to limit as x goes to, let's say, -1 of that function x, let us go to when x is -1. As you are moving from the left towards -1, our y value is -1. As you are moving from the left towards -1, our y value is also getting to -1. So in general, would say when we are taking the limit of something of this nature, x, a linear function, as x goes to a in this form means any x value. So we claim that the value is going to be, the limit is going to be a. As in this case, we will see -1, -1, 2, 2. So that is that. The same thing if we have constant function, if we have a constant function, um, let's say our function, you all know what constant function is. So if I have a function, let's say f of x is 3, which is going to behave this way. 1, 2, 3. Okay. So if we draw this function, it is going to behave this way. Now let's say we have 1, 2, 3, 4, -1, -2, -3, -4, -1, -2, and so on. If I ask you that what is the limit as x goes to, let's say, 2 of our constant function, 3. So this is our function, f of x equals to 3, just a constant function. Now, as x is approaching point 2 from the right, then we'll see that the y value stays the same. It is 3. As it is approaching 2 from the left, we see that the y value stays the same. It is 3. So if you pick another point, let's say -4, as x is approaching -4 from the right, our y value stays the same. It is 3. As it is approaching -4 from the left, it stays the same. It is 3. So we conclude that when we are taking the limit of a constant function, as x goes to any x value, call a in this case, we claim that it is going to be that constant value. So in general, we say when we are taking the limit of a constant function, as x goes to a, the answer is going to be c, or the limit is going to be a constant. All right, so please do not forget the two results. So quickly, if we use the basic limit results that we just have, limit of x as x goes to 2. Well, from what I just explained, we'll see that our answer is going to be 2. And now, this is a constant function, 5. The limit as x goes to 2 of a constant function, which stays at 5 in this case. So if we are approaching 2 from the right, your function doesn't change. It is 5. If you're approaching it from the left, your function doesn't change. It is 5. So let's say our answer is 5. All right, now let us look at some laws, some limit laws, basic limit laws, or limit laws in general. Okay, suppose we have a function f of x and g of x, another function g of x. Let them be defined for all x not equals to a. You know why? By now we have talked about, we are not really talking about at that point. We are just looking at the open interval around that point A. So over some open interval containing A, assuming that L and M are real numbers, such that when we take the limits of the function f of x as x goes to A, we have the real value, which is L. And when we take the limits of the function g of x as x goes to A, we have a real number, a real value, which is N. Then the following statements are true. So another thing is we are taking C to be a constant. Okay, the first one we are going to look at is the sum law for limits. Suppose I'm adding two functions together. I'm adding f of x to g of x. It is possible I can add a polynomial function. Or let me say I can add a linear function to another linear function. I can add a quadratic function to a linear function. I can add any polynomial to any polynomial. In fact, I can add a polynomial to a rational function, a polynomial to a trigonometric function, and so on. So we are saying that if we are adding two functions together and we are taking the limit as x goes to a, remember, both f and g are defined for all value of x not equals to a. So we are fine. Now, what the basic limit law is saying is that we are adding two functions together and we are taking the limit as x goes to a. The law says we can have it as limit of f of x as x goes to a, then we add it to limit of g of x as x goes to a. So what do we see here? We see that we move that limit can move inside into the parentheses, and we can handle them separately. Now, recall that we have claimed that we are calling the limit, the value for this, we call it L, and the value for this, we call it N. So in conclusion, we can say, let me do this. So we can say that, okay, I can take care of this. So we can say that our answer is L plus N. That is, add the value of the limit for f of x, add it to the value of the limit of g of x. That will be the limit of when you are adding the two functions together. The same thing happens when we are subtracting. So I will just write this down because it is the same thing, subtracting two functions. So we will have this. F of x can move that limit inside. So limit as x goes to a of g of x, and that is L minus L. So we have two laws. Let us move on to another one. The constant multiple law of limits. So what we are going to do in this sense is, suppose we have a function, f of x, and we are multiplying that function by a constant, right? It is possible. We have a function, and we are multiplying the entire function by a constant value. And then, if I am taking the limit as x goes to a of everything now, the law allows me to move that limit into the parentheses. Then it becomes c limit as x goes to a of f of x. Look at what I've done. I move the limit to the function and I bring the constant out. So this is c times, recall that this is L. So that is CL. So we can have something like that. The next one I will be looking at is the product law for limits. So again, if I have these two functions and I'm multiplying them together, and then I want to take the limit of that product. Now, the law says that I can move that limit. I can move that limit into each of the function and multiply them together. I hope this makes sense to you. I just move the limit into each of the function, then I multiply them together. So remember that this is given as L. So I multiply by the other one is M. So my answer is LN. whatever L is, whatever N is. That is also the same or similar to when I'm looking at quotient law for limits. So again, if I have this function f of g divided by g of x, f of x divided by g of x, I do know that my g of x cannot be zero. I cannot divide by zero. So if I am taking the limits as x goes to a, then we say that then um, um, okay, let me do this. Let me do this. We say let f of x divided by g of x such that g of x is not zero. Then if I take the limit as x goes to a of f of x over g of x, then the law says I can write it as limit as x goes to a of f of x divided by limit as x goes to a of g of x, right? And it is, remember, the whole of this is L and this is M. So again, my M cannot be zero. So that is the quotient law for limits. Now, the power law for limits. Let us look at the power law for limits. In this case, I will, in this case, I would say I have some functions f of x, and then I'm raising it to some positive integer n, right? Now, if I am taking the limit as x goes to, let's say, a, I have a function, I'm raising the whole function to an integer, a positive integer. Then I am taking the limit of that function. So what we do have is that we can move the limit inside. So we have limits as x goes to a of our function f of x, and then I can put the power on it, meaning the whole of this is given as L from our theorem, and it is raised to power n. So um, whatever L is. So I would say all for all positive integer, for all positive integer. Okay, now the last one I'm going to be looking at is the root law for limit. The root law for limit. That is, suppose I have a function f of x, and I'm taking the nth root of f of x. Now, I have that the nth root of f of x, and I'm taking the limit as x goes to a. So what the law allows me to do is, again, I can move the limit inside. So I have the nth root of, then I have limits as x goes to a of that function, f of x. And that is, again, the nth root of L. In this case, we need to be careful. So we say this holds, if, because we know that L should be positive if our n, if this n here is even, then L must be positive, right? So if n is, oh, let me put it this way. So this equals to nth root of L for all, for all L, for all L. If for all values of L, if our n is odd. I hope that makes sense. If our n is odd, then it holds for all L, because even if L is negative, but n is odd, I can still evaluate that on the real number system. And it has to be positive L. It has to be positive L or 0 if n is even. For example, if you are taking the squared root of a number, so you want it to be positive, so that means our L should be positive or 0. So let us make use of these laws. Again, let us quickly revisit these laws. We have the sum laws that says if you have two functions, you add them together, you take the limit, then you can take the limit of each function separately, then you add them. Subtraction, the same, you subtract. For a constant, you can factor out the constant, then you take the limit of the function. The product, you can say the limit of each function, then you multiply them together. For division, it is the same. Take the limit of the numerator, take the limit of the denominator, then you divide it. For power, move the limit inside. Whatever you get, then raise your answer to your positive integer. And for the root law, which we just considered, just make sure you move the limit inside, but know that that law holds for all values of L if your positive integer is odd, and it is only taking the positive value of your limit L if your n is even, positive or 0. Okay, let us make use of these laws. In this example, we want to find the limit of this function. Our f of x is 4x plus 2. Now, if you look at what I have here, I have addition. Now, the limit laws allow me to move my limit in and do this. Limit of f of 4x as x goes to -3 plus limit as x goes to -3 of 2. Now, if you remember, so here I use sum for limits. That is what I used there. Now, remember, this is a constant 4. I can move it out, then I have 4 limits as x goes to -3 of x plus limits as x goes to -3, 2. What I used here is the constant law for limits. Constant law for limits. Here is some law for limits. Okay. That being said, remember from our basic limit law, this, because x is a linear function, so we know what it is, right? As x goes to -3, that value is going to be -3. I hope that makes sense. Then multiply by 4 plus, this is a constant function too. So the limit of our constant function 2 as x goes to 3 will always be 2, wherever x is going to. it will be that constant function. So in the end, we have negative 12 plus 2, and our answer is negative 10. Done. So here we use basic limit law. Basic limit law. So that is what we use. Let us look at a bigger problem. In this case, this looks like a situation whereby we have rational function or quotient in this case. Now, we do know that we can write it this way from the quotient law for limits. So that is 2x squared minus 3x plus 1 divided by limits as x goes to 2 of x raised to power 3 plus 4. So this is from quotient law for limits. That is what I've used here. Now, remember, for this function in the numerator, I have subtraction, I have addition. The limits law allow me to move my limits to each of them, to each term. So I have limit as x goes to 2 of 2x squared minus limits as x goes to 2 of 3x plus limits as x goes to 2 of 1 divided by, I will do the same thing at the denominator, limit as x goes to 2 of x cubed plus limits as x goes to 2 of 4. Now, in this sense, we have used sum and the difference law for limits. So we can say, oh, this is 2x squared. Then we can move it out. So we have we have moved that 2 out. So we have x squared left. X squared as x goes to 2. You have to write that limiting value every time. Minus, again, I can do this. Move the 3 out. Limits of the function x as x goes to 2 plus, here I'm just going to let it remain as it is. Then here I will have limits as x goes to 2 of x cubed plus, again, I will let this remain as it is. So here I have used the power, is that power? No, I have used the constants law for limits. That is what I used here. Now, if you look at this, the next thing I will need to do is to use the power law. The power law says I can take the limit of this. So I have 2. Now, look at this. I have this. So I can just raise it to that power, right? So which is, now this x is a linear function. As x goes to 2, so recall that it's going to be 2. It's going to behave this way. Minus. Now, in this case as well, limit of x as x goes to 2. X is a linear function. So the limit of x as x goes to 2 is going to be 2 from the basic limit law. Plus, this is limit of a constant function, 1. So As x goes to 2, our answer is 1. Divided by, again, here we are going to be doing the same thing. So there it is 2 raised to power 3 plus, this is a constant function, 4. So limit of 4 as x goes to 2 is going to be 4. So finally, we are going to be okay, maybe I should write what I used here. I've used uh, the power law. Oh my God. The power, the power law for limits. That is what I used here. And I also use not that alone and basic, I also use basic uh, limits law, basic law for limit. Doesn't matter. Okay. Um, Finally, I will have that is 8, I believe, minus 6 plus 1 divided by 12. And that is so that is 2 raised to power 2, 4 times 2, 8 minus 6 plus 1 divided by 8, 2 raised to power 3. That is 8 plus 4, 12. So that is 2, 3 over 12, and that is 1 over 4. So our answer is 1/4. So that is the limit of this rational function or the uh, expression given in quotient form D. So you should pause this video and try this problem. In this case, you will see we have a function here. We have another function here, a multiply. You only need to use the um, the product law for limits and some other um, limits law to do that. So if you pause this video to answer that, your answer, I believe, should be 44. Make sure you show your work that leads you to that value. Make sure you show your work. Okay, moving on. Let us consider polynomials in general because some of you might be observing some things happening here. It is just as if we are substituting, just throwing in that a value into it and we are getting our answer instead of writing all this. Yes, that is actually what we are doing. Here we are just throwing in 2 2 times 2 raised to power 2 minus 3 times 2 plus 1 divided by 2 raised to power 3 plus 4. That is what we are trying to do. Why that is true, we observe from examples above that the limit of a function, the limit of a function as x goes to a is as if we are evaluating that function at a itself. Yes, for the two situations we are very true. However, that situation is not always true. Please, it is not always true. For example, if I say the limit as x goes to, let's say, 2 of something like 1 over x minus 2, right? So all of a sudden, at the denominator, we are dividing by 0. So it is not always true. However, that's our observation that it feels like or it seems like we are just throwing in the value of a. The good news is that it holds true for all polynomials. We know polynomials are our friend. right? They behave finely. So we can see again here, it holds true for all polynomials. At this point, you should know examples of polynomial, your quadratic function, your linear function, even um, your constant function, or polynomial of degree 3, of degree 4, and so on. So it holds true for all polynomials for any choice of A, and also for all rational functions. Remember, rational functions, we have a polynomial dividing another polynomial. But there is a catch on that. We say it holds true for all polynomials for any choice of A, and for all rational functions at all values of A for which the rational function is defined. So for example, this is a rational function, but this function is not defined at x equals to 2. So in that case, we will not be using this approach to solve the limit of this. I hope that makes sense to you. Okay, let us look at something. Suppose we have P of x as a polynomial, Q of x as a polynomial, and A is a real number. Then we want to make a claim that when we take the limits of a polynomial function as x goes to A, we claim that it is as if we are evaluating that polynomial function at the limiting point, which is A. So that is this part. Also, if we are taking the limits of, say, we have a polynomial function divided by another polynomial function. So now we have a rational function as x goes to A. Then remember that from the quotient law for limit, I can write it as limit as x goes to A of P of x divided by limit as x goes to A of Q shoot, of Q of x. And from here, I will claim that this is P of A and this is Q of A. Of course, our Q of A cannot be 0. So we have this. Let us quickly prove these parts. Let us prove this part. So let P of x be defined as follows. By now, you should know how to define a polynomial function. So let's say P of x equals to the general form. I'm writing the general form for polynomial. C sub n x to power of n plus Cn minus 1 x n minus 1 plus continues like that until you get to C1 x plus C naught. Okay, that is a polynomial function, P of x. So we define P of x in that regard, where C sub n's a constant function. Now, let us take the limit of P of x as x goes to A. So we will have limits as x goes to A of C sub n, this plus C n minus 1 x n minus 1 plus goes on that way C1x plus C naught. Okay, with that, we can remember when we have a situation like this, from the sum laws for limit, we can move the limits in. So we have limits as x goes to a of c sub n x to n plus limit as x goes to a of c sub n minus 1 x n minus 1 plus that dot 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 means and so on until the last two limits as x goes to a c1 of x plus limits as x goes to a of a constant function c naught. So again, from the constant law for limit, I can pull this cn, c sub n, I can pull it out. So we have this x to the n plus cn minus 1 limits x goes to a x n minus 1 plus dot 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 c1 limits as x goes to a of x plus, I will leave this the way it is, c. Now, look at this. I have now returned to a situation whereby I have limit of a linear function raised to a power. So in this sense, it is going to be Cn, that is just a multiplier, a constant. So this is going to give me x, it's going to give me a, right, from the basic law for limit. Limit of a linear function as x go to a is a. Then I will put the power there. The same thing, cn minus 1, that is an minus 1. Plus dot 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 c1, that's now become a plus, well, this is a constant function, so it remains a constant function as x goes to a. Now, look at this function we have here, and look at this, what we have here. Is it not the way we define our p of x, but now instead of having x, we have a. So we claim that this is exactly p of a. So that is how we prove that assertion up there. Thus, limit as x goes to a of a polynomial function is as if we are evaluating that polynomial function at a. So also, we don't need to prove the other one. That is just from, in fact, this is enough because I just proved this. So we can just use this one. So that is that. Okay, let us now solve problem. Okay, in this case, see, we have a polynomial function. Now, instead of doing limits as x goes to -2 of 3x cubed minus limit of 2 of x as x goes to -2 plus, and do the same thing for 7. Instead of doing that now, since I know that this function is a polynomial function, then I can just substitute the value of a. I hope that makes sense. So maybe you can pause the video and think about this a bit before you continue. So it turns out that you can just say equals to, just substitute your a for x. So that is 3 times -2 raised to power 3 minus 2 times -2 plus 7. So that is 3 times -8 plus 4 plus 7. So that is minus 24. That is minus 24 plus 11. That is minus 24 plus 11. So that is negative 13, I believe, if everything is correct there. So that is that. For quotient as well, all what we need to do is to plug it in, direct substitution, because we have proved here that this holds and it allows us to do this. So meaning that we just evaluate at 3. So that is 2 times 3 raised to power 2 minus 3 times 3 plus 1 divided by 5 times 3 plus 4. So that is 2 times 9 minus 3 times 3, 9 plus 1 divided by 15 plus 4. So that is 18 minus 8 minus 9 plus 1 is minus 8 divided by 19. So that is 10 divided by 19. Answer. Okay. Now let us look into other techniques for finding limits of functions. Let us revisit the function we have seen earlier in this class. This function should be familiar to you. Now, I brought this graph back to remind you of something, that it is possible to have the limits of a function. Let's say the limit of this function, for example, as x goes to negative 8, for example. At this point, you should know what the answer is. The answer is negative 6, because as you look from the right to that negative 8, your y value is going to negative 6, right? You are trying to move towards this negative 8. The y value is trying to get to negative 6. The same thing from the left, it is trying to get to negative 6. Since they are the same, then we say that limit of that function as x goes to minus 8 is negative 6. Done. But look at what we have here. This, in this function, this negative 6 is not the value of that function at negative 8. The value of that function at negative 8 is actually negative 3. Oops. Now, we are in a situation whereby this is no longer true. Let me remind you from what we have seen earlier, that if you are looking for the limit of a function as x goes to a, x not equals to a, then it is going to be the value of that function evaluated at a. And we use it. But we said that it is only true for polynomials. First, we say it is not always true. And that is the situation we just realized now. We said it is always true for polynomials, and we use that. We said it is always true for rational functions if that a is in the domain of that rational function. Now we have a situation whereby it is not true. That is, the limit of this is not equal to f of that negative 8. See, x is going to negative 8, but the limit is not the same as that function evaluated at negative 8. So I'm just using this graph to show you that you have seen it before, actually. Okay, what do we do in this situation? We can see from above that it is certainly possible for the limit of a function to exist as x equal to a when f of a is undefined. In fact, it is possible that it is, yeah, undefined completely. Here, it is defined. It's just that it is not equal to that limit. Sometimes it is that it won't be defined at all. Okay. Um, Consider the following functions. X squared minus 1 divided by x minus 1. Our x is not equal to 1 because if it is 1, then that function is not useful. It is undefined at that point. So f of x is x squared minus 1 divided by x minus 1. Consider another function g of x, which is x plus 1. We observe that these functions are identical for all values of x not equal to 1, as shown below. It turns out that if you put this function into decimals, and you put this function into decimals, it turns out that they behave the same way. They behave the same way. From your pre-calculus 1, you might have seen something like this when you were graphing rational functions. But that is not our interest at this point. So that is why I'm just providing you with the graph. So the graph of x plus 1 and the graph of f of x, which is x squared minus 1 divided by x minus 1, are identical. The only thing that we see is that there is an open point here, which is not here. That is the only difference that we can see from these two graphs. Also, okay. Now, that is because this function itself is not defined at x equals to 1. So that is why you see it is open here. It is not defined. 1 is not in the domain for that function. So that is why we remove that point. Okay? Now, but we say they are identical. What is actually happening here? Okay. Now, one more thing, one more observation is that the limit, let us talk about the limit. We only talked about the y value. Let us talk about the limit now. So as x approaches 1 from the left and from the right for this function, we realize that the limit as x approaches 1 of that function, okay, this is g of x, is 1. Is it 1? 2. It is 2. Is 2, right? The y value is trying to get to 2. The y value here, no. The y value here is trying to get to 2 on both sides as we are trying to approach this point, x equals to 1. The same thing here, the limit is the same. Limit as x goes to 1 of f of x is also 2. Is also 2. So the graphs are identical, the limits are the same. The only difference is that we remove this point for that of f of x. That leads us to a very good result. And that result is, I will come back to this. That result is that if x is not a, we know, and the graph of, the function f of x is the same as the function g of x over some open interval that contains that a, then we can make this claim that the limit of f of x as x goes to a is the same as the limit of g of x as x goes to a, which we just found earlier above. Now let us see something. If we use the idea that we are earlier by direct substitution from what we proved earlier, we are going to have this situation: x squared minus 1 over x minus 1. If we throw in 1, we are going to have 1 squared minus 1 divided by 1 minus 1. And that is 0 over 0. We call this indeterminate form. Indeterminate form. Indeterminate form. When we have the form 0 over 0. 0 over 0. Please, guys, 0 over 0 is not 0. And 0 over 0 is not 1. Okay? So, we call it a form. It is an indeterminate form. And that should make sense to you because we can't even divide by 0. Okay, now, what do we do when we are having that situation? What should we do? So let us briefly look at how to calculate a limit when we have the indeterminate form of 0 over 0. The first thing you need to do is to first establish that you have that form. First, we need to make sure that our function has the appropriate form and cannot be evaluated immediately using the limit laws. You must first establish that it has this form. If it has that form, it means you cannot just substitute or use all the limit laws that we have talked about earlier. Now, what do? Well, you need to find another function that is identical to that rational function. Okay? You need to find another function that is identical. Now, how do we do that? Well, you can try one of we may need to try one or more. Sometimes one is okay. Sometimes you need to try like 1, 2 before you can solve it. Now, you can, if f of x and g of x are polynomials, we should factor each function and cancel out any common factors. That was what we did here. X squared minus 1 divided by x minus 1. We can say this is x. Remember, difference of 2 squares. So that makes this become x minus 1, x plus 1 divided by x minus 1. So this can take care of this. So we have x plus 1. Right? So that was how we find that g of x that is identical to this. And now we claim that the limit as x goes to 1 of this function will be the same thing as the limit as x goes to 1 of this function, because we are able to find that function that is identical to that. Now, so if f of x and g of x are polynomials, the numerator is a polynomial, the denominator is a polynomial, you can factor both of them and see if you have something that we cancel out. Another thing you can do, if the numerator or denominator contains a difference involving a square root. For example, something like this. Let's say you have something like this. This numerator is containing a difference that involves squared roots. What do we do in that situation? We should try multiplying the numerator and denominator by the conjugate of the expression involving the square root. That is, in this case, the conjugate of this is root x plus 1. So I will multiply that. And lastly, if the situation we are having is such that f of x and g of x is a complex fraction, you need to simplify it. And lastly, one of these three things should work for you that will now allow you to be able to use the limit laws. Okay, I hope this makes sense to us. Let us consider some examples. Let us consider some examples. Um, evaluate limits as x goes to 3 of x squared minus 3x divided by 2x squared minus 5x minus 3. Remember that the first thing we need to do is to use direct substitution, right? But then what do you notice? If I throw in 3 here, I will have, so let me say x squared minus 3x divided by 2x squared minus 5x minus 3 equals to, so that is 9 minus 3 times 3. So that is 0. What about the bottom part? 2 into 3 squared minus 5 times 3 minus 3. Most times you can do this maybe in your head or somewhere, um, you know, on your paper. So you see this is 9 times 2, that is 18 minus 15, that is 3 minus 3, that is 0. So we claim that this function has the form 0 over 0, which is indeterminate form, right? It has this form. It is not answer. We cannot have 0 over 0 as answer. So it is a form which is indeterminate form. And what we have learned here is that when we have that situation, we can apply any of these. We can apply one of these three or more, depending on the situation we are having. In this case, the situation we have is this is a polynomial, this is a polynomial. We have a polynomial dividing another polynomial. So we can factor. Now, this is what I'm going to do now. This is step 1. I showed the form. So step two is to find that identical functional. So I will write it this way: limit as x goes to 3 of x squared minus 3x divided by 2x squared minus 5x minus 3 is the same as the limit as x goes to 3. I can factor this out, x minus 3 divided by, quickly, let us look at this, 2x squared minus 5x minus 3. You should know how to factorize this at this point. So you have 2x squared, that will be minus 6. So I can have 6 times 1, that is minus 6x plus x minus 3. You should know how to factorize. Or you can pause this and revise how to factorize quadratic expression. So this is 2x into x minus 3 plus 1 into x minus 3. And we have 2x plus 1, and we have x minus 3. So I will just bring it here, 2x plus 1, x minus 3. Ooh, look at that. We have x minus 3 here, x minus 3 here. They can cancel. And now I have limits as x goes to 3 of x divided by 2x plus 1. Now, when I have this, the next thing I will do is to plug it in. So if I do that, that will be 3. The denominator is not going to give me 0. Ooh. So I will say this equals 3 divided by 2 times 3 plus 1. Now look at something, folks. So this is 3 over 7. 2 times 3, 6 plus 1, 7. Whenever I use my limit, that is, whenever I plug it in, I don't write limit here again because I have already taken the limit now. Okay. I hope that makes sense to us. Now, this is time for you to also work this out. So try this. I put the answer there, so you should pause the video and work this problem out. The answer should be 1 divided by 3, 1/3. All you need to do is to first ask yourself, is it in this form? You must show that. Don't just go ahead and find identical function. You must first do this. That is the first step. Show that it has an indeterminate form. Now, when you do that, then you ask yourself, do you have polynomial divided by polynomial? If your answer is yes, then try to factorize. So in this case, the answer is yes. So try to factorize this just as we did here. So maybe one will be able to cancel out the other. And please note how I work here. I took the function here and say it has this form. Then I said the limit of that function as x goes to 3 is the same as the limit of an identical function, which I obtained by factorizing the denominator and canceling out. Please, that is very, very important, because we are not saying, we should not say that this function is the same as this function. That is not what we are saying. We are saying they are identical. So the limit is the same. So that is what we have been doing. And if I remind you what we did here, look at it. This function is different from this function, right? But in a way, we're able to see that when we factorize, we'll see that the graphs behave same way, right? So please write very well. Write very, very well. So step 2, we look for that identical function, and I carry my limit with it because it is that law that allows me to do that. If I have two identical functions, then their limit will be the same thing. Okay. And lastly, here I use step 3. Step 3, I use the basic, or I use the limits law, right? So, and I have this. Moving on. So if you pause the video, you should have 1/3 as your answer. Now, let us consider a situation where we have a radical in this case. So again, let us look at that function. Take the function itself. We'll see that, in fact, by looking at this, you will see that if I throw in -1 for x, that denominator is going to be 0. If I throw in -1 in the numerator, in the radical, I'm going to be having 1. Square root of 1 is 1. 1 minus 1 is 0. So I can claim that that function itself, x plus 2 minus 1 divided by x plus 1, as the form, that is the first thing we must establish, 0 over 0. So that is the first thing. Next, now, is to take that limit, the entire function, square root of x plus 2 minus 1 divided by x plus 1. And now I'm going to find, which I know is going to be equal to the limit as x goes to -1 of an identical function, which I'm going to obtain by, in this case, I'm going to multiply by the conjugate of that part having, so I just need to turn this guy to plus 1 divided by square root of x plus 2 plus 1. So that shouldn't be something new for you in this class. So I will write limit. Look at the way I'm carrying my limit because I have not used it. So I need to keep carrying it. Now, I need to multiply this. So remember, from difference of two squares, if I'm having x minus 1 times x plus 1, it is always the same as x squared minus, that is this times this, then this times this, minus times 1, plus minus 1 times 1, 1 squared. But that is when here is negative, here is positive, and they are the same, x1, x1, which is what I have here. What I have here is what I have here. What I have here is what I have here. This is negative, and this is positive. So that will be square root of x plus 2 multiplied by square root of x plus 2. Remember, square root of 2 times square root of 2 is 2. How do I know? Because square root of 2 times square root of 2 is square root of 4, which is 2. So that allows me to know that here I'm going to have x plus 2. That is the value for square root of x plus 2 times square root of x plus 2. And then minus times plus, minus 1 times 1, 1. Divided by, at the denominator, please listen, do not multiply it. Just write everything this way. Just bring the two together as it is. The reason being that, remember, we are looking for if there is something we can cancel out. So this is limit. Again, I have to write my limit. I have not used it. I need to copy it. So that is x plus 2 minus 1. So that is x plus 1 divided by x plus 1 times square root of x plus 2 plus 1. Now, look at what we have. There is x plus 1 in the numerator, x plus 1 in the denominator. I cancel 1, cancel 1. So I have limit. I still need to write it. I have not used it. Minus 1, 1 over square root of x plus 2 plus 1. So the next thing I do now is to apply, so that is the last step. is to apply the laws for limits. So just plug it in. So that is 1. I don't have any x in the numerator, so that is a constant function, which is going to be 1 divided by square root of -1 plus 2 plus 1. And that is 1 over square root of 1, which is 1, plus 1, which is 2. So answer. So again, see, once I use my limit, it disappears. I don't put it there again. Similar to once you say square root of 9 is 3, you don't put square root on this again because you have already used it. So, so this is what you should have. Okay. Now, again, you should pause this video and work this out. Work this out. Your answer should be this. Should be 1/4. Should be 1/4, I believe. Again, first look for the form. This form, if you plug in 5 here, that will be 4. Square root of 4 is 2. 2 minus 2, 0. 5 minus 5 at the denominator, 0. So you have 0 over 0 form. Then you need to multiply by the conjugate of this. And then do something, 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 then use your use your limit law and see if you can arrive at 1/4. Okay, look at this situation we have. We cannot say in this form that, we cannot say in this problem that this is a polynomial. No, the denominator is a polynomial, but the numerator is, we have a rational function minus some rational function, right? So this is a situation whereby we say we have a complex fraction, right? We have a complex fraction. Now, the question is, what should we do? First, let us see if, let us check for the form. Okay. Now, if I plug in 1 for this x here, I will have x 1 plus 1, which is 2. That is 1 over 2, which is 1/2. So 1/2 minus 1/2 is 0. If I plug in 1 at the denominator, I have 1 minus 1, which is 0. So again, I have 0 over 0. I need to report that 1 over x plus 1 minus 1/2 divided by x minus 1 as the form 0 over 0. What that tells us is that we can use any of these 3 ideas. If it's a polynomial over polynomial, factor them. But in this case, it is not a polynomial over polynomial. If it is that one of the numerator or denominator is having a difference involving square root, multiplied by the conjugates. But in that case, that isn't what we have. Okay, it is this case when we have a complex fraction. What do? We begin by simplifying. So let us simplify. Now, so this is the first step we take. We already obtained the form, so we are sure that we need to do something. Step 2, we simplify. We simplify. So let us see. Remember that if we are simplifying, it means that we are still looking for that function that is identical to the whole of this. So meaning I need to write limits as x goes to 1 of 1 over x plus 1 minus 1/2 divided by x minus 1 equals to limits as x goes to 1. Now, what can I do? To this part, 1 over x plus 1 minus 1 half. I can do this. 2x plus 1, right? Um, the denominator, then I can say this is 2 minus, I need to be careful, x plus 1. I hope what I'm doing here makes sense to you. It's just like if you have 1 minus 2 minus 1 over, 1 over 2 the minus 1 over 3. You find the lowest common denominator, which is 6, then you say, then you work this out. It's the same thing I'm doing there. So in this case, we have 2 minus x minus 1, minus times plus minus, so that is minus x, minus times plus minus, so over 2 into x plus 1, and that is 1, 2 minus 1 is 1 minus x. So I have 1 minus x divided by 2 into x plus 1. That is for this part. Now, x minus 1, I can say divided by x minus 1. This part. Well, let me do something to help us differentiate that. This part is just x minus 1. Okay. So equals to limit. I need to write my limit. I have not used it. So this is 1 minus x divided by 2 into x plus 1 times, remember this could be this, so over x minus 1. Now, if we look at the situation we have, it is not a perfect situation. This is 1 minus x. Here we have x minus 1. We cannot say they cancel. They are not the same thing. However, we can manipulate one of them. What do I mean? I can say this is limit as x goes to 1. Remember, 1 minus x, if I factor minus out, I can have, okay, let me do it this way. Firstly, I can rewrite this one as minus x plus 1. It's the same thing, minus x plus 1. Now, I can factor minus out. So I have x minus 1. Okay. Minus, I factor minus out, then I have x minus 1. If I throw it back, that is minus x. Then this, that is plus 1. I have not done anything illegal. So I will just do that here. So it then means I can write this as this. So minus x minus 1 divided by 2 into x plus 1 times 1 over x minus 1. Now they are the same, this. So I have limits as x goes to 1 minus times 1 minus 1 times 1 minus 1 over 2 into x plus 1. Now, the last thing I will do is to use, so the last step is to use the basic, to use the limit law by throwing this one into wherever I see x, right? So which is negative 1 over 2 into negative, into 1. I'm substituting x for 1, so 1 plus 1. So that is minus 1 over 2 times 2 for answer. So again, see, once I use my limits, it disappears here. I don't have it there again. Until then, you have to keep on carrying it. So, we haven't done anything strange. Uh, we have not done anything strange. Oh my gosh. Okay. We have not done anything strange. We only did what we have been doing from our previous math classes in the past, just simplifying fraction. That's it. Just simplifying fraction. That's what we've done. So pause this video and try this out first. Does it have that form? If it is so, then simplify. And then lastly, use the uh, limits law to find the limit. In the end, your answer should be -1. If my work is correct, there should be -1. So, yes. Okay. In some cases, let us keep going. In some cases, we have functions that do not fall neatly into the patterns described above. That is, they are not polynomial over polynomial. It is not that either the numerator or the denominator is having a different form of squared root, or that we have complex um, friction. Or let's say, in quotes, it is not a situation whereby we have 0/0 form. Let us put it in that form. Let us put it in that form. It's better that way. Now, what do? It does not neatly fall into that pattern that we have been working on. So what do? Let us see. So we say evaluating a limit when the limit laws do not apply. What do we mean by limit law? Does that mean that we cannot say, let us find the limit of this and add it to the limit of this? Remember, if I have 4x plus 2, and I say find the limit as x goes to 1, I only need to say this is limit as x goes to 1 of 4x plus limit as x goes to 1 of 2. And I will say this is 4 times 1 plus 2. And this is 6. But in this case, can we do that? Let us see. It turns out that no. Why? Look at this. If we are substituting here to be 0, it means we are having 1/0. Again, here, if we are substituting x for 0, it means we are having 5/0. No, 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 no. That is not helpful. So do not do that. Do not do what we did here, like taking the limit one by one. We cannot do that. The limit laws do not apply in that situation. What do we do then? We first need to take care of that fraction inside. So, what do I mean? We need to say this is, so here the form, not the form 0/0. Oh, not the form 0/0. What do? Well, let us simplify that fraction. How can we simplify the fraction? You can use any method you know, but the common denominator there will be this, and I will have x minus 5 plus 5, I believe. Let's see. this x minus 5, this 1. Yes. So that is what we have. Just combining these two fractions. That's what I've done. Okay. Algebra. So that is limits as x goes to 0. Now I have x minus 5 plus 5. That is x over x into x minus 5. Now I can say this is x L1, x L1. So I do have limits as x goes to 0 of 1 over x minus 5. And now I can apply the limits law. So by throwing in this 0 there, that is 1 over 0 minus 5. And my answer is negative 1 over 5. Answer. Or 1 over minus 5, which is minus 1 over 5. So, not bad, right? So, again, pause this video and solve this. I believe your answer should be this. I worked this out, so if my work, I believe the answer is 1 over 4. So, go ahead and solve that. Okay. Now, let us look at a special case evaluating a one-sided limit using the limit law. Evaluate each of the following limits if possible. We know what one-sided limit is. Look at this problem. We want to find the limit of square root of x minus 3 as x approaches 3 from the left. Now from the left, this is 3. Any value that is here is less than 3. And if we plug it in here, it will make this guy to be undefined. We don't want that. So we claim that since the function we have is undefined, for all x less than 3. For all x less than 3, that is from the left, then it only means one thing. It only means one thing. Oops. Let's see. Okay, it only means one thing that's implied. Then, okay, then the limits as x goes to 3 from the left of square root of x minus 3 does not exist. That is what it means. If you remember the graph of this guy, the graph of x, if you remember how it is, right? You remember the domain of that, and you remember how it looks like. Now, when we have this case, transformation, you remember it means that it is it has been transformed or it has been shifted. It means the graph is shifted to the right by 3 units. So it means you have something like this. That is the way it is, right? This is the graph of square root of x. This is the graph of square root of x minus 3, shifted to the right by 3 units. Now, look at this. You cannot find the limits as x comes from the left because you don't even have any function here. So it does not exist. Okay. However, can we find the limits as x goes to 3 from above, from the right? Yes. And what is the answer? So we can say it is 0. It's getting to 0. So this is 0, done. Or you just use your basic law, plug in 3 here, that is square root of 0, which is 0. I hope that makes sense. Meaning that when we are looking at limits, one-sided limits, the domain is very, very important to know if that function is defined at that point. Okay. The next thing we want to look at is evaluating a two-sided limit now using the limit law. Two-sided limit using this limit law. The first example I'm giving you here is piecewise function. Look at it. That function is defined as 4x minus 3 when x is less than 2. That is, let's say this is 2. On this portion, on this domain, it is defined as 4x minus 3. And anything greater than 2, it is defined as, that is, anything here above 2, it is defined as what? X minus 3 all squared. Now, evaluate this. Limit of f of x as x goes to 2 from the left. Now, that is, what part of this function are we going to use? It is going to be this. Limit as x goes to 2 from the left. That part of the function where x is less than 2 or where x is coming from the left to 2 is what we are going to use, 4x minus 3. And then we just plug in the value. So that is 4 into 2 minus 3. So our answer is 5. 8 minus 3, 5. Now, what of from above? From above, now we see from above, it will consider these parts. So that is limits as x goes to 2 from above of x minus 3 all squared. So, which is, we plug in 2 again, 2 minus 3 all squared. So that is minus 1 squared, which is 1. Now, look at this question. What is the limit of f of x as x goes to 2? I will claim that it does not exist. Also, the limit from the left is not the same as the limit from the right. That means the limit as x goes to, that means the two-sided limit does not exist for that function at that point. Okay, what about this piecewise function? Given that f of x is defined in a piecewise form like this, evaluate the following limits. Limits as x goes to -1 from the left of f of x. The question you need to ask yourself is, what part of that piecewise function, what part of that function is going to have to consider from the left? Well, this is x less than 1, minus 1 rather. That is all the values less than -1. This is -1, all the values less than -1. And that is what you are considering from the left. So it means you will use that here. So that is, now you can just plug it in now. So remember it is -1. So, but you have negative here. So that is minus into, our x is -1, -2. So that is 1 minus 2, which is -1. That is the left-hand limit. The second one is from the right. Now let us study this function again from the right. Here is saying x is exactly -1 there. That is not what we want. We want this part. X is greater than -1. That is, all the values greater than -1 from the right. So In that case, we will use, so that is equal to limit as x goes to -1 from above. That portion is x cubed, x cubed. And we just need to substitute now. So that is -1 raised to power 3. And it is -1. -1 times -1 times -1. That is -1. What can we say? The limit from the left is -1. The limit from the right is -1. I can conclude that the limit at that point is -1 because they are the same. Okay. Um, hmm. So there is a problem with, okay, let me, hmm, I will change this to, let's see, I change this to -1. Let me put it that way. -1, let me see my computation. -1 here, -1, -2. So that is +1 -2 -1. Okay. -1 raised to power 3. So that is -1. Okay. Yeah. Oh, maybe since I'm not considering that, I can leave it the way it is. Never mind. Okay. So that is how to deal with that. Um, limit from the right, limit from the right, limit from the left, then we can conclude if they are the same, that the limit exists and it is exactly what we have for both one-sided limit. Okay, evaluating a limit of the form k over 0. The other time we have 0/0 form, but what happens when we have k over 0? K is a number that is not 0. So when we are dividing it by 0, again, remember, we cannot divide by 0. So it is a form. So how do we handle this form? It is different from when we have this form. We have dealt with that. But when we have a number, let's say 1/0, it is a form. So how do we deal with this form? All what we need to do is to separate the part that leads to 0 in the denominator. We need to separate it and see. As in this example, look at this. X minus 3 over x squared minus 2x has the form k over 0. Or you can just put the value there, which is, if you plug in 2 there, that would be -1 over, if you plug in 2 here, that would be 4 minus 4, that is 0. So this is the form. Now we say the way to handle this is that you need to separate the part that is leading to 0 at the denominator. So to do that, I can say the limit as x goes to 2 from the left, x minus 3 divided by x squared minus 2x. I can factor the denominator, x minus 3 divided by x into x minus 2. I can do that. Now, the part that is leading to 0 is actually this part. So I can write it as is the same as limit as x goes to 2 from the left, x minus 3 over x times 1 over x minus 2. Is that true? I can separate it using multiplication. It's fine, right? um, what I'm saying is if I have, let's say, 2 over 3 times 4, I can write it as 2 over 3 times 1 over 4. That is what I've done. Okay. Now, in this case, look at what I'm going to do. Remember from the limit law, when I have multiplication, it can become something like this. Limit as x goes to 2 from the left of x minus 3 over x times limit as x goes to 2 from the left 1 over x minus 2. The product law for limit. Now, here, if I plug in 2, I will have 2 minus 3 over 2 times. Here, what is the limit of this? If I plug in 2, I'm going to have 1 over 0. That is what is causing the problem. But let us think about it. As you are taking x values here, minus 2, as you are taking x values very close to minus 2, meaning you are taking negative values, negative x values. As you are taking those values very close to negative 2, and you are saying 1 divided by those values, now you will see that they will be becoming smaller and smaller and smaller and smaller. For example, this is what I'm saying. Right? Minus 2 minus 0.1, right? Minus 2 minus 0.01. Minus 2 minus 0.001. When you are using that, you are getting closer and closer to that negative 2. So if you are dividing this now by 1, so your number will be becoming smaller and smaller and smaller, right? You can pause this video and just put this in your calculator to see what I'm talking about. Now, it ends up that what you are going to have is, it keeps going that way, then it is negative infinity. And now this is minus 1 over 2 times minus infinity. So you are multiplying a very big number, a very small number by negative 1 over 2. So it becomes positive infinity. That is my claim. So this is the limit of that function in this case. So use that idea to answer this problem. So because I don't want this video to be too long, I will cover the squeeze theorem in our next video. So just let me end this video at this point. I hope you enjoyed the video. So you can like it, you can share to your friends who might find this video helpful. So see you in my next video. Bye-bye.